In this video, we're going to be learning about hemiacetals and acetals, which are functional groups that form when we add an alcohol molecule to an aldehyde or ketone through an addition reaction. So let's see. When we talked about addition reactions during our alkene chapter, we had our double bond here, and we added a small molecule like Br2, Cl2, HBr, or water. And then once we added that molecule, we formed single bonds between the X on one carbon, the Y on another carbon, and then that bond between the two carbons becomes a single bond. And so that was our addition reaction for an alkene. For our aldehyde, it is easier to visualize by holding our carbonyl sideways like this, much in the way that we drew our alkenes in that previous chapter. Then we're going to line up our alcohol molecule. And so we have our OH from our alcohol, and then whatever our group was attached to the alcohol. So you see that little prime here? That's just to differentiate that whatever carbon chain was attached to that O from this carbon chain that was attached to that C. So we were trying to just differentiate between that carbon chain that's attached to that O and this carbon chain here. So when these two molecules add together, it doesn't matter what else was on that C. What's important is that how we're lining this up. We're lining up the O from the alcohol to the carbon, and this O from the carbonyl lines up with that H. So when we form this here, we're going to form our bonds, and then that's going to break this bond between the O and the H on the alcohol, and then that becomes a single bond here. Now that we've added that across the double bond, we have new functional groups. What used to be the carbonyl here is now an ether. And what used to be this alcohol becomes an ether. So our carbonyl, trying to color code a little bit, carbonyl becomes an ether, and then the alcohol becomes an ether. Becomes an ether, that's an alcohol. What the heck did I just write? So the carbonyl becomes an alcohol, and the alcohol becomes an ether. So that's an addition reaction. That was an addition reaction because we conserved all of our atoms. We just merged these two molecules together. We can react this molecule now that we have an alcohol and ether sharing a carbon. That's known as a hemiacetal. That means hemi is half, like a hemisphere is half of the Earth. So we can take this and form what's a fully fledged acetal by reacting with a second molecule of alcohol. This second reaction is a condensation reaction. We'll be seeing lots of condensation reactions once we get into our carboxylic acid chapter and, of course, our biochemistry chapters. This is our first condensation reaction. In our condensation reaction, we are going to be adding these two molecules together, and then a small molecule is lost in the process. So as we add this on, this O comes in here and attaches, and then that H and all that comes off and forms water. So maybe I should use a different color pen. Let me erase this so we can clearly see what is happening for the second part of the reaction. So we have this H here, and this OH comes off and forms H2O. This RO comes in here, and the O sticks. So now we have two ethers on our acetal. So condensation reactions, two molecules come together, and then a small molecule like water is lost in the process. So we're going to practice identifying our hemiacetals and our acetals. So we're going to start with an aldehyde or ketone, and then after we add an alcohol, then we're going to be looking for a hemiacetal, which will have one alcohol group and one ether. Then we're going to recognize our acetals, we're going to be looking for two ethers sharing a carbon. And then these alcohols and also have to be sharing a carbon. That's important. So they have to be attached to the same carbon. They're on different carbons, it's just two separate functional groups. It's not this special hemiacetal or acetal. Notice how acetal kind of sounds more similar to aldehyde. If you're going to be looking on YouTube or other online resources, they're going to differentiate this further into hemicetals and ketals, depending on whether it started life as an aldehyde or if it started life as a ketone. Hemiketones would be starting life as a ketone, and ketals would start life as a ketone. As far as you're concerned, though, we're going to just simplify it and just pretend that it's all hemiacetals and all acetals. So you only have to care about hemiacetals and acetals, recognizing that hemiacetals have an OH and an ether, and acetals have two ethers. So here's a practice problem for you. Hemiacetals contain which two functional groups? Go ahead and pause the video and select something. So hemiacetals contain an alcohol and an ether. That's exactly what I said just a second ago. And here's another practice problem for you. Go ahead and classify the following molecules as either hemiacetals, acetals, or neither. Go ahead and pause the video and try to decide this on your own. Unpause the video when you're ready to check your answers. Okay, so for this first one, we have an alcohol and an ether sharing a carbon. That's really important. That's going to make this one a hemiacetal because we have an alcohol and an ether sharing a carbon. For this next one, we have this ether and this ether sharing a carbon. Two ethers sharing a carbon. That is an acetal. For this next one, we have an alcohol. That's an ether. Brain hand disconnect. This is the alcohol. We have an ether and we have an alcohol, but they are not sharing. So this one is neither. For this one, this is cyclic, but this is an ether, this is an alcohol, and they are sharing a carbon, and so that's a hemiacetal. Hemiacetals and acetals occur naturally in many products, and we will be revisiting this heavily once we get into our carbohydrates chapter. This is the structure of lactose. Lactose is a disaccharide. It has a acetal carbon here. You can see the two ether groups, two ethers, sharing a carbon, and so that makes it an acetal. And there's also a hemiacetal over here because we have an alcohol and we have an ether sharing a carbon. We can have reactions between an alcohol functional group and an aldehyde functional group that exist within the same molecule. These are intramolecular reactions because the molecule is long enough in order to complete this reaction. So your final product will either be a 5-member ring or a 6-membered ring, meaning like a pentagon shape or a hexagon shape. Any rings bigger than this are a little bit loosey-goosey, not optimal in shape, and then things smaller than that are also not optimal in shape. The carbons are too strained with their angles, so they're not too happy. So look for, by member, I mean that you will have an oxygen as one of the corners in the ring. So that's why I didn't say like cyclopentane or whatever. So you just have to look for pentagon shape or hexagon shape. You can decide how many members are going to be in your chain through counting. And so you can see here that's a carbon number 1, 2, 3, 4, and then the oxygen is the 5th member of the ring. And so this would mean you're going to have a pentagon shape, and then you're going to have carbon number 1, 2, 3, 4, and then this is that 5th carbon that they drew over here. So that's the 5th member of the ring is the oxygen, but that 5th carbon is still off of the carbon number 4 as the substituent. So we can have this intramolecular reaction. Carbon number 1, where the aldehyde was, becomes your new acetal carbon. Well, that's your hemiacetal. But we know that hemiacetals can react again in another reaction in order to form acetals. A little foreshadowing into our carbohydrates chapter. We will have these intramolecular reactions within our sugar molecules in order to go from a straight chain form of our monosaccharides into a cyclic form of our monosaccharides. So this is the structure of glucose, and so this is carbon number 1 up here. That's carbon number 2, 3, 4, 5. And so if this oxygen reacts, that's going to be the 6th member of the ring. So that 6th member of the ring is the oxygen. And this 6th carbon over here is a substituent on the back. So this is that. So that little 6th carbon sticks back there. But this carbon here is our new hemiacetal. And then this hemiacetal can react with other glucose molecules in order to form acetals when we form polymers or disaccharides. It will be super fun once we get to the carbohydrates chapter to see all of these reactions again. Let's go ahead and try to practice drawing the structure of the acetal formed by adding 2 methanol molecules to butanol. Go ahead and pause your video and try to draw the structure of the molecule from adding 2 methanol molecules to butanol. Okay, I'm going to start off by drawing butanol. Butanol has 4 carbons, and it starts off life like this. That's a 3. Alright, so that's butanol. And once I add 1 of these, we have to remember that this is the part that's going to attach to our molecule. So we're going to have, let me switch colors. No, not that. Okay, I'm going to switch colors. Colors are awesome. So this is going to be sticking on to where the aldehyde was. I erased the H on that aldehyde, didn't I? Why did I do that? Give me back my blue pen. So that did start off life with the aldehyde H, and so that H that was on the aldehyde still needs to be there. So it's really this OCH3 here that's going to get added on twice. We know it's going to be an acetal, which means 2 ethers. And so that's the other part of our ether there. These addition reactions can be reversed, and so we can break apart our acetals, which were formed from a condensation reaction. We can break apart our acetals through a hydrolysis reaction. Hydrolysis is the opposite of condensation. Hydrolysis literally means like water cutting. So hydro means water, and then lysis, means to cut. Lyse means to cut or split open. And so it's like little water scissors. Water scissors go snip, 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 and cut those off. And you can reform your aldehyde or ketone and reform your alcohol molecules. And so there's some color coding here. And so these are going to reform alcohols. Over here. So we can undo this type of reaction. So here's some practice problems to summarize, to re-go over some of our reactions that we've covered in the lecture so far. Go ahead and pause the video and try to work out the products for the following reactions. Unpause the video when you're ready to check your work. Okay, so for our first one, we have to recognize that this is an aldehyde. Kind of drawn on its side, but we can see that it is an aldehyde because it has this bond to an H here. And then once we reduce an aldehyde, we'll end up with a primary alcohol. And so we will end up with 2 carbons, primary alcohol, like that. So for our first one, we need a primary alcohol. So I'll go ahead and cross those out. For our next one, we have our aldehyde again. And this time we're exposing it to an oxidizing agent. aldehydes oxidize into carboxylic acids. That's a pattern that you can recognize. So that second, this H here becomes an OH. So we will have a carboxylic acid. Here's a second problem for you. Go ahead and pause the video and try to work out these products. Unpause the video when you're ready to check your answer. Okay, so our first molecule here is a ketone. Ketones can be reduced. That means making more, make less bonds to O, more bonds to H. And so we are going to take our ketone. Let me take my ketone here. We're going to make less bonds to O and more bonds to H. This is a secondary alcohol. So we need to form a secondary alcohol, cross those out. Now we have this same ketone, and oxidizing agent means we're going to make more bonds to O, less bonds to H. This ketone has no bonds to H, so we can't go any less than 0. We can't have -1 bonds to H, and so this one can't oxidize. So we're going to say no reaction. Secondary alcohol, no reaction. So we have learned about several different reaction patterns, and by memorizing these patterns or understanding these patterns, we can kind of see some greater patterns. Addition and elimination undo each other. Condensation and hydrolysis undo each other. And oxidation and reduction undo each other. So we've learned some oxidation and reduction patterns for aldehydes and ketones and alcohols, and in our next chapter for carboxylic acids, we'll experience them again. Condensation and hydrolysis we'll be experiencing a lot in the next chapter as well. And then addition and elimination we've encountered in a few different chapters.